Okay, so I'm recording this one also. So you can see that this is the this is like a two-part course, you can say. This is not a, but they are independent courses. And in the first part, I explained the very basics about the Savonius wind turbine, and the data we used for Savonius wind turbine 2D case was exactly from the this paper, this report from Sandia Laboratory. This is US laboratory, like many laboratories, like a NASA, and similar in a similar way. These laboratories for the renewable energy. So Blackwell et al. Was the first person who actually made the one Savonius wind turbine. They were like having the 3D blades, but we simulated in the in two-dimensional way. Okay. And then after understanding, the first part is the understanding that if you understand very well the data and the background, then you can actually go for simulation. Okay, that's a very important step that is missing from the many CFD simulations. So first thing is that you must understand what is this that particular geometry, a particular case, and its physics. Okay. So after going through the data, we created the CAD modeling of the 2D case and then tetraprism meshing, and we set up the problem and then run the solution. And after running the case, we got the data, and that data need to be processed, simplified. Process means that we have to take the every data. Okay, so data is large. It's a very large database that we have to convert into the meaningful data. Like for example, from the time at a different times we can have the like a torque value, but what we need is that we need a one average value for the whole revolution of the one turbine revolution. So that's what we did also as well in this case. So then in 2D case, I also gave the some background of the renewable energy that you can see on the slides. I can share the slides again with everyone. And a general introduction of the renewable energy, some numericals are also given so that you can get the idea. And then the wind energy was followed by the general introduction. We went through all the basics, the generic graph for the wind turbine performance, and this generic graph is not some drawing. Actually, this is based on the various testing of the different type of the wind turbines, and not only the like a Savonius turbine is given here. So not only that, this is like a done for the one case. This is done for the various cases. And data here is actually every data, and that represents that class of the wind turbines. But this was done, I think, in the back to the 90s or 80s. The new wind turbines, Savonius turbine, they are performing likely over there. Okay, so that is like a change of technology or improvement in technology, and the understanding of the physics of the different turbines. And similarly, Darius turbine, you can see here, these all are they are the vertical axis wind turbines, and then the most efficient wind turbine that you can see on the large scale, those are the horizontal axis wind turbines, and they are producing like a 7 megawatt or more. Okay, and the small wind turbines like a Savonius wind turbine, they are limited to the 5 kilowatt, and they are only used for the domestic purposes. Okay, so then I went through the different theories, the data of the Blackwell et al. This is a picture from that same reference. Then we did the everything, and finally we got the results. Okay, so the basics were all covered there. So in this course, in 3D course, not only that I'm going to cover not all the basics, but I'm going to cover the basic required for 3D case. Okay, so in 3D case, what I did is that this is over here. Okay, so this case starts from, this is from some different reference, and the reference that I'm following here is the first reference, and the same reference actually got a data for the DR validation from the second reference, and this was published in 2005, and the first reference was published in 2018. So the general theory of Savonius wind turbine is given here. The data, it was like invented by the Sigurd Savonius in 1920s. And after that, from the same reference, we have the data, which is given here. And the geometry you are seeing here is actually made in the by myself, and that will I will be teaching in the course. And this is over given here. Okay, design modeler, and this is just picture of the same file with the plates, and plates on the top and bottom. Data is given here, and the domain shape and the size is also given. Then I'm making the inner domain, the wake domain, and afterwards the fixed domain and the final geometry. This is the mesh generation parameters that were applied, and we finally got the mesh in this way. So data actually for the consideration. This is from the reference number 1. So I even copied the important data that is given directly here. You can see here. So TPSP ratio was for validation is a 0.286. Although the best performance for the 7-inch turbine is around value of 0.8, 0.8, 0.9, 0.7, varies from the turbine to turbine. But for the validation case, the tip speed ratio, and tip speed ratio is actually the ratio of the wind turbine rotational speed and divided by the wind speed, the incoming wind speed. This was 0.286, and they also given that the velocity of the wind is 6 meters per second, same in the same paper. And omega that's also they define directly, so 10.4 radians per second. So that all values I put there. And the y plus value we kept is a less than 5, same as in our case, but only difference that in this case they have the first cell height of 4 into 10 power minus 5, and in my case this is a 4 10 power 5 into 10 power minus 5. I didn't check the paper actually for these data. I created mesh myself. Okay. They put the 11 10 layers, sorry 15 layers. I put the 10 layers there. My y plus value is maximum is a 5 and average value is less than 1. Okay. So and then the data which they are showing, actually this data is over here 0.286, and for this is over here, this is, and at this point the if I reverse the data from the chart to the like a tabular form, I got data at this point around 0.067. Okay. And for that I use the one software that is free to use, webplot digitizer, and from there I directly went on this point. This point is like highlighted here in the, this is like a point where I place with the mouse, and that simply gives me data. Like if I click on the view data, which you can see here, so the data is shown here. Okay. So at approximately 0.286, the value of the my torque was this is actually CP was 0.0659, that is a 0.066 around. Okay. And then from the CP, I reverse engineer again. So from reverse engineering, I have the power of the wind turbine. Okay, that is the power in the wind. And then I went to the power of the wind, the turbine that is producing the CP into P air. The formula is given. I will be showing you the other formulas. And from it, I got the wind turbine power. From wind turbine power, I use the formula T into omega, torque into omega, and I got the torque value. So torque value through reverse engineering, this is 0.0659. And when I got data from the CFD, the value is a 0.067. So 0.0659, if I get the error, so 0.05059 minus 0.067 and divided by 0.0659, sorry, 0.0659 minus so error is around 1.66%, not significant. Okay. So error is only point around, you can say it's a point like a 2%. And they have like got the data in this way. So they started mesh with the 3 legs to the 6 legs. In my case, my mesh is 1.97 million. That is the 19 legs. Okay. So their mesh is like a far finer than the mesh given in the paper. Secondly, this is not a way to like to get the mesh independence. Mesh independence should be like that, that or anybody should be like going through the one mesh, and second mesh they should double of the size of the previous mesh. Okay. So 3 legs, then the 6 legs, then the 1.2 million, then 2.4 million. Okay. So with this much change there, I'm not able to see any significant difference. Okay. And secondly, the time step study, they made the time step study like a 0.007, and in my case time step is 0.001, that is a 1 degrees per one time step. Okay. And they are using around 4.5 degrees per one time step. That is even again very like a very rough approximation. Okay. But anyhow, I'm able to replicate the original data that was given there. Time step study, like a time step, how to calculate time is also given there. And finally, this is my simulation. And you can see here that we have the simulation and animation ready also. So if I go to animation and if I just play back for last, I run the case for the more than 5 time steps, and now this is the last 5 time step that where I'm actually recording data and animation at the same time. Okay. So for the torque plot, I'm going to record at least 5 cycles and then every data. Right now, I average only 1 cycle. Okay. So best way or the recommended way is that given in the high quality journal papers is that you should like every data at least for the last 5 cycles. So first 5 cycles will be run and we will not monitor any data. And last 5 cycles will be data that we are going to monitor and then average out. Okay. So if you take a look on animation, you can see like this. Okay. So you can see, actually what I did is that I only recorded the every 5 cycle. Okay. If I slow it down, the speed, if I can slow it down. So here. So I recorded animation for, I solved the case for 1 degree per 1 time step, but I recorded the data for the every 4 or 5 cycles. Okay. Let me change the speed and now run the case. Okay. If you increase the speed, then this will be look like in this way. Okay. Any questions? So, Sama, any questions? And did you find it useful or not?
I think it is very useful, Cyril. I had a very simple question. Are you using dynamic meshing in this problem?
No, no, this is sliding mesh. Because if I use the dynamic meshing, then dynamic meshing is used for the cases where we don't have the option for sliding mesh. Okay. And sliding mesh is more accurate, and the recommended way by the software like ANSYS, Fluent, they recommend the sliding mesh for turbomachinery. Number one. Number two is that we use the dynamic meshing when we are actually simulating the like a starting torque values. Like wind turbine is starting at that point when you want to start the wind turbine, you did it with the directly wind forces. For example, when the turbine is stationary, and you want to see the starting behavior. Okay. At that time, the sliding mesh cannot work because the starting RPM are varying. Okay, and they depend on the incoming wind speed. So at that time, we use a sliding mesh. But sliding mesh again will be circular motion. That will be circular motion definitely. We need to make the two domains again. One is like a rotating domain, one is a fixed domain. But at that time, we use the dynamic meshing. But dynamic meshing is used for the wall motion, some irregular motions. In that case, dynamic meshing is used. And secondly, our third point, I would say that dynamic meshing will have a lot of problems like a negative volume. You have to set them, and time step you cannot run the case with this time step. You have to put the time step maybe 10 power minus 6, okay, to stabilize the solution. So the data, if you get like from both cases, they will be same data, and recommended way of running the turbo machinery cases with the fixed RPM is that the sliding mesh. Okay, so it's a sliding mesh, not dynamic meshing.
Okay, thank you. Thank you, Cyril.
Okay, so like you want to run the case with dynamic meshing for some particular reason, for some particular case, or
Actually, Cyril, I have to work on impellers,
mm-hmm,
centrifugal compressors,
mm-hmm.
and I was wondering what uh, models are, specific to modeling the impeller problem.
See the
Yeah.
the like you will see the able to see a screen or not?
Yeah, I'm able to see your screen. Yes.
Okay. So, just give me one thing. I'm going for the very old paper. Uh, I'm just showing you. Okay. So this is a very old paper by the John Denton. He is was in the Cambridge University. Then he retired actually. So that's why I'm saying he was okay. So he actually was the person who pioneered the work on the turbomachinery. Okay, especially his work on the mixing plane. Mixing plane actually is a method that uh, does not require the multiple blades passages, and it works it will mix out the flow from upstream component the outlet, and for the downstream component is inlet. Okay, so it will mix out means that it will select the different planes on the your inlet. Let's say if you are talking about the downstream component, so at the different lines, circumvention lines, it will apply the every data on those lines, single value on the single one area location. But it will create the different let me draw it. Okay. So for example, I have the if we are working on the compressor, compressor will have the first will be the rotor, then we have the stator. Okay. In the centrifugal compressors, we have the centrifugal impeller, and then we have the fixed plates or guide vanes. Okay, if they are the guided diffuser is there or without the guide vanes diffuser. Okay, so that is called the blade diffuser or the vaneless diffuser. Okay, so let's say this is the rotor here, and then we have the stator here. So and this is circular. If you take a look from the front view, this is in this way. Okay, hub and then the blades. Okay, so I here I have drawn the side view. So what will happen is that in the mixing plane, it will create the different radial locations. That is around lines are circumferential. Okay, so on these circumferential lines, what will happen is that they will every data and they apply the single data over there. So means that the data is averaged out. So data can vary on the circumference from the upstream component, but once we average them out, the one data will be there on the single line. Okay, that data will be applied on the downstream component through the interface. Okay, so from the beginning of the whenever whoever actually invented these all things, that's why we call the CFD modeling, not the we are solving in an actual way. It's a modeling. Okay, so we go for the model that is the best suitable for our cases, like a heat transfer case. So suitable model, what would be suitable model that we have gone through those things. Scientists are through the different research paper. You can, if you go through different papers and see what people have done, okay, you will get the idea. Okay, so even the software company that ANSYS or Stars CCM or OpenFOAM, they recommend these things. Dynamic meshing is used when you are solving the case that motion cannot be simulated with the help of the sliding mesh. Okay. And secondly, sliding mesh is a transient case. Dynamic meshing is a transient case. So you only run the dynamic meshing or sliding mesh when your case is actually a transient case. Okay. For the mixing plane, we are assuming cases like a design point. The case is like a steady state. It's behaving as a steady state. So mixing plane approach is very good actually. Okay. But for wind turbines, we cannot use a mixing plane. There's just a lot of a discussion will be we can here we can do here. If I go through everything and every aspect of the turbo machinery, but by understanding what is done, what is being used, how people are using, you will get a very good idea. Okay, so I would suggest only one thing, that you should not be listening to any YouTuber, especially. Okay, a YouTuber or some immature person on the some Facebook forum. Don't maybe they are very good people, but that's not authentic. Authentic thing is like a software help guide. You should be looking at these people who have done the pioneering work. Their papers are the people who are doing now the advanced work in the same field. Okay, so not you don't listen to me, don't listen to anybody else. Listen to the some authentic sources. Okay.
Sure.
Okay, so I think you are clear about the things about your case, but
Yes.
definitely you
Yes.
need some
Yes. Yes.
time. You need to time that how to get geometry, then how to process geometry, then how to make the meshing. So maybe you can go directly turbo grid, or you can make the meshing in the ANSYS meshing also. So tomorrow I am like teaching a ANSYS meshing course, and that's very cheap actually for Pakistani students, not very high price. Okay, so you can go through that course also. I'm going to share the link also in the group if you like to join it.
Okay.
Okay.
Sure.
This
Sure.
course will be held. That this course will actually will give you lot of idea about the turbomachinery modeling, and why I'm using the
Okay.
sliding mesh, why not the other methods, when to use other methods. So I will discuss these things as well in the course.
Okay.
Okay. So maybe you
Sure.
can join this
Sure.
course also. Okay. So
Okay.
today the price is like half for this course if you join today. Then from
Okay.
tomorrow price will be like the full price.
All right.
Okay.
So what's the price of the course?
It's a 4,000 rupees for Pakistani people. For like I shared the like in the group. So
Okay.
the price,
And the course is about meshing only?
the meshing course is different. That is from the tomorrow. This
Okay.
course is from the Wednesday, 20 August. So meshing course is
Okay.
only 1,500 for Pakistani people if registered by today.
Okay.
I think date is
All
still
right.
there. This course is 4,000 only. Uh,
Okay.
uh, Professionals they pay 7,000, but for the foreign like international student they have to $35 and $50. That's a slightly higher price.
All
So
right.
because I'm from Pakistan, so that's why I'm trying to give the most benefit to the
All-
my country fellows.
Sure.
So tomorrow
Sure.
this price will be 8,000. Okay, from 4,000.
Okay. Okay.
Okay. So let's see that if you join you will get benefits. Okay, and thank you for joining for this session. Actually I like to
No problem.
interact with the people, so
Yep.
I try to give the sessions regularly every week. Okay.
Okay.
Okay, thank you.
Thank you.
Thank you.
Thank you,
See you,
Sujal.
see you then.
See you. See you. Bye bye.
Bye bye.